Okay, so the application of Gauss's law helps you find electric field problems and look at them through a different approach. And this is important because of literally how simple it is. Okay, so using what we learned before, we have here a spherical surface of radius r, okay? And what we want to do is find the electric field outside of this surface, okay? So what we do is we can go ahead and draw a Gaussian surface with radius a, okay? So here we have the Gaussian surface, and let's go ahead and change this to a. Okay, so Gauss's law states that the flux of a surface, which is E dot dA, okay, this equals the total charge enclosed, okay, which is, oh, my bad. Okay, so this is Q over epsilon naught. Okay, so that charge enclosed is the total charge of the surface. Okay, and as we already saw, we can remove the dot product of E dot A. Okay, because the dA, which is this over here, which is if you remember the little section here on the surface. Okay, and the E, which is also, I'm going to go ahead and write that down just so that we don't forget. Okay, this is the dA. Well, let me write it with lowercase. So this is dA. There we go. And the E is also heading in this direction. Okay, just like we saw previously, the electric fields. Okay. Now, because E is a constant, we can go ahead and pull that out of the equation, okay? So remember the equation that we had previously with the integral, all right? So what we can go ahead and do is E integral dA, okay? And well, that, as we also previously saw, is equal to E times 4 pi radius squared, which in this case is the A. And well, that's due to the equation of the surface area of a sphere, okay? Now, the electric field along any point along this Gaussian surface is equal to the charge enclosed, which turns out in the formula, let me go ahead and write it down. E is equal to 1/4 pi epsilon naught times Q, which is a charge, over r squared. Let me write it down a little bit better. So we have 1/4 pi epsilon naught Q over radius squared. All right, let me erase this one. And I'm going to go ahead and put it in a square because this is the formula that we want to be using. Okay, and while breaking this formula down, the Q and the epsilon naught, so we're going to be talking about this Q as well as the epsilon naught. Those come from the Gauss Law, okay, and the 4 pi r squared comes from the formula for the surface area. Now, I just wanted to make that 100% clear, just in case anyone was a little bit confused. Okay, so I'm going to go ahead and circle this, okay? And this is equal to Gauss's law. And let me go ahead and put that in blue. So this, as well as this, is equal to the formula for sphere surface area. Okay. All right, so just to be clear, within this, pause. One, two, three. Okay, and well, the solution here, it also has a direction in which it points outside due to the fact that it is a positive charge. Remember that it always goes from positive to negative. So basically what we have here is the solution written down and transformed with Gauss's law, right? And well, basically that's it. That's the solution for an electric field for a sphere with a total charge of Q, which is what we have right around here, okay? So basically what we did here in just a couple of minutes is Gauss's law, and it's its way of really simplifying things. And well, without this law, this would be a pretty difficult problem just for electric fields. And well, it's a really simple way of breaking down problems. And yeah, it's a pretty simple solution. Hope you guys liked it. Please do leave a comment with any questions or feedback you might have, as it helps me make better videos. And remember, please like the video and subscribe to our channel. That way you can support us and help us grow.